Now we are going to be talking about planar graphs. So before we move into planar graphs, we'll touch on equivalent graphs first. So equivalent graphs or isomorphic graphs contain the exact same information. It's just rearranged or displayed in a different way. So when I was talking about our subgraphs, we had that some information had been removed, but nothing had been added. But when we're talking about equivalent graphs, they contain the exact same information, just in a different form. For example, have a look at this graph here, and then have a look at this one here. These, while they look different, and they are different in some ways, they actually display the exact same information and connections because they're equivalent or isomorphic graphs. Because we can see that this connection here has simply just been stretched and moved around to the outside. So planar graphs are graphs where no edges cross over each other, or there is an equivalent graph where there are no overlapping edges. So this graph technically is a planar graph because there is an equivalent graph where there are no overlapping edges. It is just not in a planar form here because these edges overlap. You can see that intersection, that cross section that we've got in the middle because the edges are crossing over each other. But here we do have an equivalent graph where there are no overlapping edges. Where if there was not an equivalent graph with no overlapping edges, then it would be a non-planar graph. It would not be a planar graph. But these graphs here are technically both planar because this one has an equivalent form where we can make sure there are no overlapping edges. So what can we notice about this graph? We can see we have 4 vertices. You can count the blue points. We have 4 vertices, 1, 2, 3, 4, 5, 6. We can see that we have 6 edges. The other bit of information that we can find out from here is that we have 4 faces. So what is a face? A face is like a defined or distinct enclosed separate region of a graph. So that is an example of a face. That is an example of a face, as is that. And it's also important to remember to consider the outside area as well, because that's another distinct region of the graph. So we can see here that this planar graph has 4 vertices, 6 edges, and 4 faces, which brings us to Euler's formula, which you might have heard of. So Euler's formula for planar graphs tells us about the relationship between the number of faces, edges, and vertices of a planar representation. So Euler's formula is only relevant and only applicable to the planar representation of the graph. And Euler's formula is V plus F, take E equals 2, or the number of vertices plus the number of faces minus the number of edges equals 2. So Euler worked out the exact mathematical relationship between the number of vertices, faces, and edges for any planar graph, and this is what they found out. And we can actually see that that does hold true in this planar graph. Number of vertices, we have 4. Faces, we have 4. Edges, we have 6. So 4 plus 4 gives us 4 plus 4 gives us 8. Take away 6 gives us 2. And because 2 equals 2, we know that Euler's formula does hold up in this situation. So we've talked about a whole bunch of different things, and now we're up to the idea of walks. So walks are the idea that you can actually move around a network. So I could move from this point to this point along this edge. I could move along this edge. I can move around and around on the edges. So the idea that we can move around the networks is often referred to as like walks. And there's certain language that we use to describe those certain movements. We have open and closed walks, open and closed trails, open path, we have cycles. We can look for the shortest path weight-wise. There's all of these different things we can do, all of these different ways we can move around a graph or a network. And my challenge for you is to construct your own glossary of definitions with examples to solidify your understanding of these differences, because we're not going to go through them today. So make sure you get that clear in your mind, because that can be really good easy marks for short answer or multiple choice questions in an exam. So one thing I did mention that we are going to go into in a bit more depth is looking for the shortest path. And when I say shortest, I'm not talking about the shortest number of steps. I'm talking about the shortest weight-wise. So we want the lowest weight, whether that's the lowest cost, the lowest time, the lowest amount of kilometers. We're looking for the lowest weight. So like I said, when we're talking about the shortest path, it would probably actually be more accurate to say like the lowest weight. Because for example, we're going to be talking at the moment, we're going to be looking at finding the shortest path between two different vertices. First, from B to E, and secondly, from B to G. So let's take B to G for an example. We can see that we have one edge connecting B to G. Because it has one edge, it might appear to be the shortest path, but that has an associated weight of 15, we can see here in our graph. Whereas if we took a different route that might potentially have more steps to get to B from B to G, but would it have a lower weight? That's what we're asking. So let's have a look at for B to G. So B to G possible path options. We could start from B, go to A, go to F, and then go to G. And because they both, even though there's multiple edges connecting F and G, because they both have a weight of 1, we could actually take either of these options. So it doesn't matter which. So they both have a weight of 1. So taking that path from B to A to F to G, that has a weight of 3 and 9 and 1, which gives us a total weight of 13, which we can actually see is already a lower weight than doing 15. So what's our next option? We could go from B to C, over to F, and then again over to G, which has a weight of 6 and 3, and then also 1, which gives us a weight of 10, which is actually even lower than our first option. And we also, like I said, have that option of going straight directly from B to G, and that has a weight of 15. And because we are looking for the shortest path, or like the shortest path as in lowest weight, we can actually see that B to C to F to G is actually the best option because it minimizes the length, weights, liters, whatever it is that this network is representing. It has the lowest weight, so that is actually the quickest or most efficient or most cost efficient route, even if it seems like B to G via this edge here would be quicker because it's simply one edge. But when we're talking about the lowest weight, that's actually not accurate. So that's interesting to keep in mind as well when we're talking about the shortest path. We're not talking about the shortest number of steps or the shortest amount of edges. We're actually talking about the lowest weight. So if a connected planar graph has 8 edges and 6 vertices, how many faces does it have? We actually don't even need to be able to see or need to draw this to work this out. And that's because of, I hope you remember, Euler's formula, which states that the number of vertices plus the number of faces minus the number of edges will always equal 2 in a connected planar graph. So we know that we have 6 vertices. We don't know the number of faces. That's our unknown value. And we know that we have 8 edges. So all that we need to do then is substitute into our formula. And we can see that 6 take 8 will give us -2. And then to isolate f by itself, we add +2 to both sides. And that tells us that a connected planar graph with 8 edges and 6 vertices will have 4 faces.